Great. So welcome everyone. I'm glad today that I host my PhD supervisor, Salvatore Capozziello. Salvatore got his PhD in 93, if I remember correctly, in Napoli.
Yeah.
And since then he had traveled here and there, and I think all around the world, from the US to Europe to Japan, China. He is a full professor in Napoli at the University of Napoli, Federico II. And he's been president of the Italian Society of General Relativity for 5-6 years. And now he's the director of the cosmology section of the newly founded Scuola Superiore Meridionale in Napoli. Today, he's going to talk about going beyond the standard lambda CDM model using cosmography. So, yeah, thank you very much, Salvatore. The floor is yours.
Thank you very much, Kostas, and thank you to the organizer for inviting me. I am very happy for this very, very nice initiative that is very interesting in this period. Okay, so what I would like to discuss today with you is just a general picture in which I would like to show you that despite of the fact that there is a plethora of possibilities in order to explain the standard cosmology and then the huge flow of data that are coming from cosmology, by cosmography, we can have a further approach by which it is possible not to ask for the model a priori and then try to see if it is possible to give some hints in order to reconstruct a nice cosmic history from the early to the late time. Okay, so probably I will say something that you people know very well, but I would like just to give a sort of didactic approach to this, and then to try to convince you that by cosmography cosmography could be a useful tool in order to address several problems in the today cosmology. So I would like just to have a sketch of the standard cosmological model. Then I would like to discuss some shortcomings and open issues that are in this model. And then I would like to convince you that there is the necessity to go beyond the lambda CDM in order to try to understand the dynamics and the cosmic history in a self-consistent way. So I take into account essentially two approaches. The one which is a very phenomenological approach, which is trying to unify dark energy and dark matter, in a sense that without considering what is the fundamental constituent of dark energy and dark matter at particle level, we would like to understand if it is possible to consider dark energy just like an engine capable of accelerating the universe, while dark matter as an engine capable of clustering structure. And then starting from these very, very simple statements, if it is possible to find out some self-consistent model capable of describing what is going on into the dynamics. Then I would like to discuss with you a little bit the modified theories of gravity, in particular the Trinity gravity and several possibilities that are on the market, because some of you are very expert of this. And then the main part of the talk is connected with the cosmography, which could be extremely useful in order to reconstruct models. And then by cosmography, we can try to see a sort of inverse scattering approach to the problem. And starting from this, this could be also a useful tool in order to see what you can retain and what you can discard into the discussion in this plethora of possibilities. Okay, so come to the problem. As you know, the cosmological principle is at the basis of the standard cosmological model. The universe is especially isotropic, and the universe is homogeneous at a large scale. All of you knows very well this. And in particular, the standard cosmological model is based on general relativity, on the Bianchi identities, on the possibility to take into account the Friedmann-Lemaitre-Robertson-Walker metric. All of you knows very well this stuff. And the topology of the spatial part of this could be in some sense fixed according to the density of matter that is present into the model. The energy momentum tensor gives the dynamics of matter. And in this respect, we can construct the Friedman equations, the energy conservation, the equation of state, and then the density of the cosmic spaces can be essentially reduced to a sort of normalized density parameters. So the problem, the model is very simple in its mathematical structure, but as we will see, there are several shortcomings that are questioning the validity of this model at any scale. So the first evidence for the accelerated expansion, as you know very well, are the type 1 supernovae. And as you know, all of you knows very well these two pictures. It seems that the accelerated expansion exists, and it is questioning the previous picture by which the model should be decelerating. Then we have the problem of cosmological constant, where it can improve the Friedman equation, and the cosmological constant could be considered inside the expansion of the Hubble rate as a component, and such a component could be in some sense related with the so-called dark energy, as we will see in a moment. So the cosmic pi is based on this concordance paradigm, where you can see that most of the cosmic pi is essentially unknown due to the fact that dark matter and dark energy for 95% cannot be known at fundamental level. Okay, so with this status of art, let us discuss a little bit which are the observational probe for this. And in particular, the first is based on the supernovae. The supernovae could be extremely interesting. Why? Because they give the distance modulus, and according to the Phillips law, they are capable of fixing in a very detailed way the luminosity distance. And then we can reconstruct in some way the luminosity distance, and then you can reconstruct the Hubble parameter, taking into account this approach, and then you can take into account this as a first approach in order to have some good result in this perspective. So as you know, the supernovae can be better and better constrained. In this paper by Skolnick et al., you have that it can be improved, the reliability of the cosmology, the supernova cosmology, and in particular, you see that all indications are toward the accelerating universe if you take into account a sort of phase space where from one side you have dark energy and from the other side you have dark matter. Omega lambda and omega m say essentially this. Okay, so another probe, very important, as we was saying, next year will be the 6th anniversary of its discovery, is the cosmic microwave background radiation. The cosmic microwave background radiation gives us a very, very detailed snapshot of the early universe, and in particular, it can take into account the temperature anisotropies. The cosmic background can be essentially reconstructed as a function over a sphere, and then according to the spherical harmonics expansion, you can say that for any of the multiple expansion, you can fix a given phenomenon, and according to this, you can have a very, very detailed picture of the universe at any scale, and in particular at any epoch. So, as you know, the Planck collaboration gives this very, very important picture in which for any peak of this view graph, you can fix a particular phenomenon at cosmic scales, and as you know, in the left side of this picture, there are a lot of physics, and we hope that, for example, by the stochastic gravitational waves, we could try to have more information in this very unknown region of the spectrum. Another interesting, I will go quite fast in this part because I wanted just to give you a summary of what is on the ground for the observational information. Another important, very important probe is given by the baryonic acoustic oscillations. The baryonic acoustic oscillation can be, in some sense, a sort of cosmological ruler. Why? Because, as you can see, the baryonic acoustic oscillation scale is of the order of 147 megaparsec, so they are larger than the scale of any virialized structure. And then, according to this, the baryonic acoustic oscillation can give us essentially a good probe for the background that people is investigating. As you know, after 100 megaparsec, it is very difficult to get some large-scale structure. So the baryonic acoustic oscillation is very good in order to fix the scale at which the background should be compared. Furthermore, there are the observational Hubble data. This is a big matter of debate because it is connected with the cosmic chronometer, and in particular it could be extremely interesting in order to fix the value of H0, and it could be also considered one of the main source connected with the Hubble tension that we are going to discuss very soon. Another important probe is connected with the growth rate factor. Why it is important? It is important because it is in my opinion, it is one of the best tool in order to probe how subhorizon scales can be compared with the background. And in particular, it could be a probe, an extremely interesting probe, this sigma 8, on how the cosmic fluctuation can be related with the structural formation from one side and with the given background. So it has a very, very important role, and also the tension in sigma 8 is extremely interesting because it is connected with the fact that the growth of perturbation could be essentially probed directly from the large scale structure. Okay. So let us come to the problems. In particular, as you see, we have a big problem with fine-tuning. The big problem with fine-tuning is related with the fact that we have to explain this 122 order of magnitude between the density of vacuum from one side and the observed cosmological constant. By the way, we have also the coincident problem, because the coincident problem is essentially related with the fact that with these very, very different histories, why we have so teeny number in order to indicate that observations are essentially indicating omega lambda of the order 0.7, omega m of the order 0.3. Also, if the evolution is very difficult. So it is a big issue that should be understood in some way. So we can try to improve the lambda CDM model in order to address this kind of problems. And as you know, there are several proposals on the market. You can combine, for example, the cosmic microwave background with supernovae. We can combine a cosmic microwave background with BAO, and you can have several ways in order you can take into account several probes and try to fix better and better the equation of states ruling the dark energy. And as you see, for example, if you take into account Pantheon and the cosmic microwave background, you can restrict more and more this coincidence between the various data. In particular, you can consider, for example, the well-known Chevalier-Polarsky leader parametrization. In this case, it is the simplest generalization of the lambda. In that case, you are considering just a linear improvement of the redshift according to the fact that at a high redshift you cannot retain the standard lambda CDM, but you have to improve the fact that by this two-parameter approach you can try to fix the data. The approach seems quite promising, and in particular if you use a supernova, cosmic microwave background, BAO, and H0, you can try to restrict the area at which you can have some information. In particular, you can see here that, for example, if you use omega CDM or if you use CPL models, according to the sample of data that you can take into account, as much as you are improving the data, you can get a better information on omega, on omega M, on H0, and on W. And then, according to this, you can try to fix better and better the cosmological model. However, there are several other problems. From one side, we have dark matter, and from the other side, we have H0. So dark matter is a big issue. Why? Because it seems that at the moment there are no particles that which can totally explain dark matter. I'm in contact with the people working for the direct detection of dark matter in Gran Sasso, and they are very frustrated in this moment because there are no WIMPs, no axion, and so on. All the evidence are very teeny, so dark matter in some sense should be in some sense rethinked. You have to rethink essentially the problem in order to understand phenomenology, because the problem of some missing matter exists, but the possibility to detect some particles out of the standard model of particles is very difficult. From the other hand, you have the H0 tensions, and all of us knows very well the story. And this can be connected with some errors, or it is the evidence of some new physics. There are some conceptual flaw, and so on. So also in this case, we have some problems that from one side are very exciting, from the other side are very frustrating, because it seems that if you want to have a unified picture of the universe at the local scale and at a large scale, you have to confront with this approach. So it seems that kinematics from one side and dynamics from the other side seems to have different results. In particular, you have that the very local universe, the value of the H0 is completely different with respect to the value of H0 at Planck, with respect to the Planck measurement. Okay, so as you know, this dark matter problem exists, and it seems that at the microphysical level, the correction to the Einstein equation seems not to be related directly to some new particles. Okay, from the other side, you have that the H0 tension could be, it is the very hot topic of these years. And as you know, it exists. There are some proposals. I mentioned some of my proposals with my collaborators, but the problem, according to my perspective, is far to be fully understood from one side and fully addressed from a very final, with some very final result. Also, if there are some claims by Rees, by Freeman, from several people, which are the debate is very high in this moment. Okay, so with this status of art, now let us come to directly to the topic of this talk. Is it possible to go beyond the lambda CDM? Lambda CDM is very good as a today's snapshot of the universe, but if you want to reconstruct the story, we have several problems. So we can have two main approaches, according to me, and I would like to describe these two approaches. From one side, let us try to see if it is possible to unify dark energy and dark matter, taking some example from the standard physics. And I would like to give you two examples in this perspective, which are the Chaplin gas extension and the logotropic dark energy. And both of them are taken by the matter physics, because they describe, in some sense, some situation where you can have condensed matter. And then, starting from this analogy, let us try to see if it is possible to find out similar results also at cosmological level. From the other hand, you can have extension of lambda CDM. So I like to say that there could be extension, which means that you can recover in some way Einstein gravity. So Einstein gravity is nothing else but a particular case of some more general theory, particular F over theory or some scalar tensor theory. On the other side, you can have alternative to this, and this alternative to this could be connected with the other invariants, which could be the non-metricity, the torsion, and so on. We can have also extension which are connected with electromagnetism. For example, there is this de Broglie-Proca approach, there are some massive photons, and so on. So in some sense, we need models which are capable of solving the issue of concordance paradigm, which could be coherent with a self-consistent cosmic history. So, in some sense, as you see, let us try to see if it is possible to simplify the problem and then try to reconstruct what we are really observing and then try to reconstruct a model. So, instead of proposing a model and then trying to see if the results agree or not with the observational results agree or not with this model, let us to change our philosophy. So in a sense that what data are saying, and according to this, is it possible to reconstruct the final cosmological model, a comprehensive cosmological model? And so, as we will see, cosmography could be very interesting in this perspective. So instead of searching for new particles, let us try to see dark matter can be nothing else but clustering properties of large-scale structure, while dark energy means reproducing the accelerating behavior of the Hubble flow. So the goal is just to reconstructing the cosmic history, and we can match from one side to the other side the matter dominance and the accelerated and then the dark energy dominance at any redshift. And then essentially we have to compare cosmography at the late and then redshift of order 0 and early and then redshift very large with respect to 0 epochs. So with this very, very simple statement in mind, let us try to construct some models. In particular, we considered this model, this Anton-Schmidt model. What is this Anton-Schmidt model? It's nothing else but the fact that you can consider the so-called the physics of crystalline solids. We borrowed this from standard physics. We have a very nice discussion with Anton Schmidt, and we see that there are some interesting properties of this approach which are related with the standard of dark energy and dark matter. In particular, the physics could be based also on analogy. Please remember that inflation is based on the fact that the transition, the phase transition are happening in condensed matter and in solid state physics. So according to this, we tried to do the same, but considering the late time universe. So what is an Anton-Schmidt fluid? An Anton-Schmidt fluid is a fluid where the pressure is given by this equation. As you can see, this equation is a relation between the pressure and the volume. So we have some characteristic parameters, which are these beta and gamma parameters. and they say how you can pass from a phase to another phase. So you can have a vanishing pressure and then a matter-dominated phase, a transition epoch when the volume V is equal to this V0, and then this is a transition epoch, and the negative pressure, which is an accelerated phase. And then a single fluid, obeying this Anton-Schmidt equation of state, can describe the whole evolution according to the volume. So we tried to do this but at cosmological level. So we have done this, and it was extremely interesting, the fact that if you consider the density of this kind of fluid, you can reconstruct in a very, very straightforward way these logotropic cosmological models, which was first announced by Chamanis in 2016, can give the possibility to describe, at least in a very rough way, the cosmological dynamics. And then you can see that when rho, the density is very large with respect to 1, we have a dominance of matter. When rho is very little than 1, we have a dominance of the so-called of the analogous of dark energy. So we worked out this problem, this model. We constructed the Hubble expansion rate according to this, and as you can see here, we can get essentially an effective equation of state, but based on a physical analog model by which you can have essentially the behavior connected with the clustering of structure from one side, with the deceleration parameter from the other side, and with the acceleration of the structure. So in some way you can fix all the various cases. In particular, you can see you can use the supernovae, the BAO, the Hubble data, and so on. And according to this, you can fix the confidence level with respect to this Anton-Schmidt parameter. I want to stress that this is nothing else but a phenomenological model, but it is interesting to see that it can be borrowed directly from the standard physics. Okay, let us come to the second part of this approach, because the same can be done, as you know very well, by modified theories of gravity. I want to say that modified theories of gravity means modified with respect to GR, while extended means that by some extension you have to reproduce the standard GR. So we have essentially GR, the TEGR, the teleparallel equivalent general relativity, and the STEGR. It depends on the geometric invariant that you are using in order to fix the model. So cosmography, in my opinion, but it's just a general feeling, cosmography plus some gravitational waves could discriminate essentially among concurring gravitational theories. As you know, there is a roadmap for the gravitational waves, and in particular, you can see that fixing the behavior and the characteristic of the various gravitational waves, you can fix also the kind of theories where you can go. So what I want to say is that this huge amount of different theories, in some sense, could be fixed at fundamental level, taking into account the gravitational waves, but at cosmological level, taking into account some reliable cosmography that it is capable or not to reconstruct phenomenology, as I'm going to discuss in a moment. In particular, you know very well this kind of picture. There is the geometrical trinity of gravity, in which, depending on the representation, you can get the same dynamics. And essentially, you taking into account torsion, curvature, or non-metricity, you can have various situations where the dynamics of general relativity, the dynamics of gravity could be in some sense represented. Okay, as you know very well the story, we discussed it in detail. what is the effect of curvature, what is the effect of torsion, what is the effect of non-metricity. But it is interesting to see that despite of this very different geometrical meaning, you can get essentially the same dynamics. Okay, so let us see how this kind of theories of different picture or extended different picture could be in some sense fixed by cosmography. So in particular, let us take into account the simplest extension, which is F over gravity. You see that in F over gravity, it is essentially general relativity, but with some more curvature. And the matter energy momentum tensor can be improved with some effective curvature energy momentum tensor, which is strictly related with the further degrees of freedom that you have curvature. And then what you get is that according with this picture, you can have that our dark energy behavior can be essentially connected with the form of the F of R that you can take into account. If you see this picture, the effective dark energy is given by the curvature, and it is interesting to see that as soon as F of R is equal to R, immediately you recover the standard GR plus the cosmological constant. Okay, so the same, you can do exactly the same in FT teleparallel gravity, but also in this case we have to be very careful because FT and FQ gravity are second order theories, while F of R gravity in metric formulation is a fourth order theories. So there are several details according to this, but as you can see also in this case the statement is very well posed, and also in this case you can have a similar result because you can work out your cosmology. So then at the end of the day you get that your effective dark energy is given by the fact that you can fix the form of FT, and according to the form of FT you can recover the dark energy behavior. These very well known results from several years. We know very well this kind of result. You can do the same also with non-metric gravity. In particular, also with non-metric gravity, in this case, you are relaxing the possibility that your model is connected with isometries. Also in this case, you can assume zero curvature and zero torsion, and then the geometry is just given by non-metricity. These are the main geometrical ingredients that you have in this case. And also in this case, you can work out in particular, you can take into account the coincident gauge. As soon as you are considering the coincident gauge, you are recovering GR, and then you are recovering equivalence principle and the isometries in this case. But when you are doing this, also in this case, you get that the standard approach where dark energy can be given by the form of your FQ is strictly is immediately recovered. So this is just a panorama on the various possibilities that you can have in order to improve the lambda CDM model. But in this amount of possibilities, the problem of cosmic evolution should be addressed by a model-independent approach. So cosmography could be useful to design because it is based only on the convergence of polynomials for the luminosity distance. This set taken by gravitation by Steven Weinberg. So already in 1972, this kind of problem was very clear, and the problem of what is the good, the optimal cosmological model was in some sense related with how much information you can reconstruct taking into account the luminosity distance. So what is cosmography? Cosmography is nothing else but the Taylor expansion of the scale factor. where you can consider a cosmographic series. So clearly you have to take into account the fact that in this cosmography you have to consider the fact that you are assuming that the universe is given by differentiable functions, and the cosmological principle is working, at least in the simplest cosmographic approach. It works. And then, as you can see here, the luminosity distance depends on the entries that you have into this series, essentially. So the Hubble expansion rate is given in this way, and according to this, you can reconstruct some interesting cosmographic objects which are related with this kind of expansion. So there are some limits and there are some advantages for this. So the limits are the fact that as soon as you are taking into account some Taylor series, it is restricted to the modulus zeta minus 1. So in some sense, as soon as you are considering data sets where you are considering high redshift, immediately the approach fails if you take into account this Taylor expansion. So this finite truncation could give rise to several propagation errors. And so also in this case, the debate of the validity of the cosmography is very, very debated. But if you take into account rational polynomials, these rational polynomials could be extremely interesting. Why? Because in that case, you can have that the convergence could go further this strict limit, which is z equal to 1. So according to this, it is very well used in approaching, for example, the black hole horizon. So in this case, this kind of polynomial, the rational polynomials are used. Here I will go to discuss two kinds of these polynomials, but there are several possibilities. In particular, I will discuss the Padé polynomials and the Chebyshev polynomials. In particular, Padé polynomials are nothing else but the ratio between two Taylor series, and essentially the Padé polynomial is fixed by the entries that you have in this Taylor series. So in particular, you can reconstruct the luminosity distance based on the Padé approximation of the luminosity distance, and the convergence is fixed according to this n and m parameters, which are saying you what is the degree of approximation that you are taking into account. In particular, here you have some examples of this, and immediately you see how Taylor and Padé can converge or not converge according to the fact that you can take into account several proposals. In particular, it is interesting, as far as we understood, that if you have that the ratio is between a polynomial where the numerator is higher than the denominator, in that case you have a good convergence, and this could be reliable in order to give us some interesting result. In particular, another approach could be based on this Chebyshev polynomial, because the Chebyshev polynomial could be in some sense more interesting, because in that case you have some recurrence relation, and then according to the recurrence relation you can fix step by step the various redshift, and then it is very good in order to construct the Chebyshev polynomial. In my opinion, are very good in order to construct a cosmic ladder where any step of the cosmic ladder is given by a particular polynomials that you can take into account. Another interesting point of Chebyshev polynomials is that they are normalized, and then according to this you can have a sort of a series where you can consider strictly the orthogonality, and then according to this orthogonality you can fix step by step the series that you are going to construct. Okay, so taking into account these two tools, and to finish my discussion, what we want to see is if using Chebyshev polynomials and Padé polynomials, it is possible to fix the forms of Fq, Ft, and F of R. In particular, to fix some models which are related with this extension or modification of theories of gravity. And in particular, we can compare the different cosmographic techniques. You can see here, in particular, how the various parameters H0, Q0, and J0 could be taken into account. And in particular, as you can see here, you can have also a taste on how it is better considering Padé or rational Chebyshev with respect to the Taylor one. In particular, it seems that, for example, if you take into account a 2-2 Padé or a 2-1 Padé, you can have a good convergence and then give interesting issues which can be related with the observation. So let us try to give some example of this approach. In particular, consider F over gravity. If you consider F over gravity, you can convert the derivatives of this. And then the interesting point is that just considering the time derivatives in terms of the redshift, and the same you can do in terms of the curvatures. So the of the air can be given in these terms. And then you can reconstruct the Friedman equations in terms of the redshift. So this is just the algebra that we need. You can assume some priors. In particular, you can assume that at certain point you have to reproduce that your effective gravitational coupling should reproduce the standard Newton constant, and this is one of these. And you can construct some bounds for the cosmographic parameters. And as you can see here, by the Padé approximation, in this case we use the 2-1 Padé approximation, we get something which is in some way reliable, because as you can see here, H is the normalized Hubble constant is 0.7, Q0 is minus 0.5 essentially, and J the jerk is more or less 0.6. And then, according to this, construct a consistent approach for giving the upper bound values of the cosmographic parameters in this perspective. In particular, in order to match at best the data, and the data that in this paper it is described in details, we see that if you take into account an f zeta of this form, you see that these are the numerical values of f zeta, and this is the best fit, the best analytical match that you can have with this kind of data. So this is nothing else but a test to see if the approach is workable or not. So you can, as a further step, you can try to see if it is possible now to match data with this analytical cosmographical reconstruction, and essentially the answer is quite good, because you can get that several of the main topics, in particular the models, those described in these papers, could be in some sense reproduced, taking into account the cosmographic approach that I mentioned before. And you can fix also some constraint at the cosmic microwave background, because you can fix priors at local scale and the priors at the cosmic microwave background scales. And finally, as you can see here, you can see that if you relax some assumption, you have to understand how the difference, the ratio, between the effective G and the standard, the Newtonian G, are converging or not, according to this. In particular, you can compare Padé versus Taylor approximation, and at third order, in particular, you have this very big difference between the Padé and the Taylor approach. So, as you can see, Padé it seems much more reliable than Taylor in order to reproduce the good behavior of what we are going to observe. So, in particular, you can compare the FOR gravity and the lambda CDM gravity, and these are the results. In particular, you can compare an FOR reproduced by the Chebyshev approximation, an FOR reproduced by the Padé approximation, and the lambda CDM. And these are the results. And as you can see here, the comparison, this kind of comparison can give us also a taste of how it is possible to go over the lambda CDM. In particular, this could be extremely interesting, you know, for this DESI data, which seems to indicate that there is at certain point some difference with respect to the lambda CDM, and in particular, this could be interesting in order to be compared with this kind of approach. In particular, then we can do the same, exactly the same. I don't want to bore you much more, but we can do the same exactly with this FT gravity. Also, in this case, you can take into account the Friedman equation. You can get some initial condition fixing some priors. You can do the same also in this case, and you can have a numerical reconstruction of the FT function, which can be obtained from the third order Taylor approximation of the luminosity distance. And also in this case, you can get a cosmographic reconstruction, and the same is, for example, for FQ gravity. For FQ gravity is also very straightforward in this paper. Together with Rocco D'Agostino, we fixed a sort of model independent approach in which this FQ gravity could be fully reconstructed, but taking into account the data. Here you have the discussion that you have done. In particular, you have seen that if you take into account a power law plus a constant, in particular, you have some very reliable reconstruction of this FQ with respect to the lambda CDM, and you can fix also, in particular, the forms of the function, and then according to this you can see if it is possible in some sense to fix in a sort of phase space of parameters which are the parameter which are good with respect to those that can be excluded from the cosmographic analysis, and then with respect to the data. Okay, so coming to some conclusion and perspective. So cosmography is nothing else but a procedure. Is a procedure to reconstruct the universe, the universe expansion in a sort of model independent way. So the lambda CDM could be assumed as a sort of prior of the model. The adoption of rational polynomials could be interesting because it could be useful in order to match the late time behavior with the early time behavior, and this cannot be done taking into account the standard Taylor approach, because Taylor approach is very good at late time but is not good at early time. For example, the calibration of the Padé polynomial or the rational Chebyshev polynomial can be compared with data, and it is possible to conclude, for example, that Chebyshev polynomials reduce very well the systematics. Recently, we brought another paper in which we used the Bézier polynomial or the logarithmic polynomials, but also in this case, the approach could give a good reduction of the systematics. Another point is that this modified gravity cosmography could give rise some hints in this discussion, because the equation of states can be in some sense recovered completely from a very genuine geometric point of view. So fixing the equation of state, you can get the form of the extended gravity, and then it could be also an indication on what kind of theory of gravity could be reliable. My suspect is that in order to have a good information, you need also some fundamental information which can give related, for example, with the gravitational waves, because the gravitational waves are very fine in order to fix the form of the theory. So finally, what next? What next? We need a multi-messenger approach in order to understand better phenomenology. We need an extension of cosmography, through extension of cosmography at high redshift. And in particular, we need also a way to compare cosmography with the cosmic microwave background. And in particular, it could be extremely interesting to see how much cosmography could be related with the tensions in cosmology, and how they can alleviate these tensions that probably could be connected with the fact that you can improve the details as soon as you are improving the cosmography. And furthermore, if it is possible, having a sort of gravitational wave cosmography, because in this case you can have something which is giving us a sort of tomogram starting from the very beginning up to now, which could be related, for example, with the stochastic background of gravitational waves. And I think that that's all. I think that we can finish here. Thank you so much.
Thank you very much, Salvatore, for the nice talk. Are there any questions from the audience?
Hi, very nice talk. Can I ask a question?
Yeah, go ahead.
Okay, very nice talk as always. It's a very interesting approach. But I was thinking as you were discussing the method, I wonder if there's been any studies. As you know, there are many degeneracies in modified gravity. I wonder if this method can possibly be used to try and distinguish or to break that degeneracy. You know, maybe to establish maybe a goodness of fit in this reconstruction, since it depends on higher derivatives. I don't know.
So you mean if it is possible to remove at certain point some degeneracy, but by cosmography, you mean?
Yes, but the cosmography could say. Sorry, please continue.
No. Yes, I understand the point. I think that cosmography is just a toolkit, nothing more. It cannot solve the problem at the very, very fundamental level. I think that the best way is combining this with why gravitational waves? Because gravitational waves are in some sense related strictly with the characteristic of the gravitational theory that you are considering.
Yeah.
So I trust more in gravitational waves than in cosmography, for sure. But cosmography is better if you want to have a sort of a general reconstruction of what is going on. So at certain point, we have a big issue. One is cosmic history, and the other one is what is the final theory of gravity. So we have to. This is the I think that this is the very very the shortcoming that we have. So we have to compare fundamental theory from one side and cosmology from the other side. So we need a fundamental cosmology at certain point, but not just related with some very strange theories, but related with data. As we know, in our Cosmoverse, we are doing this.
Exactly.
This is the point. This is the point. I hope to have answered your point.
No, perfect. No, it was my suspicion, but anyway, I wanted to get your opinion on that. Thanks so much, and again, very nice talk.
Thank you.
Thanks so much.
Thank you.
Anyone else? Yeah, if not, I will. Is there anyone else? because someone.
May I also ask a
Yeah,
question?
go ahead. Yes.
Thank you very much, Salvatore, for this nice overview that you gave to us. As you know, we are working on compact objects, strong gravity, and then also the production of gravitational waves. So would you now, from your studies, tell us what you think might be a worthwhile modified gravity to study in that strong gravity regime?
It is possible to connect this with the strong gravity. This is your question?
Yes, and precisely. And then what you kind of suggest, what would be a nice theory to study?
Yes, this is a very, very important issue, because this approach, in my opinion, is just an infrared approach. So it gives us just the very, very large scale approach. But I think that the main struggle is at the strong field level. And I think that at strong field level, this is just my opinion, you can solve the problem just considering some very compact astrophysical objects, for example, neutron stars or black holes, which have some signature which could be not be explained in other ways from one side. And from the other side, we have the problem connected with the gravitational waves. In particular, I know that there are several stars at the moment that cannot be explained by standard theory of stars, as you know. Jutta, you know very well this point. So there are very strange stars, for example, that are too large in order to be compared with the Chandrasekhar limit or with the Eddington limit. Or there are several other black holes that could be, in some sense, that are anomalous. I think that the answer is there, because in this kind of object, you can see how much you are in agreement or not with respect to the general relativity. I think that retaining stubbornly general relativity is not good at this moment, because general relativity is a very good theory, but it should be improved in some way. Or you can find out some new particles, or you can you should find out some extensions. But I think that considering geometry should be the very natural approach in order to extend the general relativity, or at least try to see if there are some more degrees of freedom that could be in some way taken into account. So cosmography, in my opinion, is a sort of a very, very naive approach, but is a naive approach which could be useful in order to discriminate among several concurring models. So you can fix at least the class of models which can work or not. But I think that the prova regina, the main issue, could be based on the fact that you have to explain something like black holes or gravitational waves at some fundamental level. I think that this is the main. However, the point of cosmology remains, because cosmology needs self-consistent models. But probably, for example, I have a my personal opinion on the tension is that we are comparing two very different issues, for example. Because if you compare the Hubble law at local scale, this is kinematics. This is a good kinematics. But if you are considering the Hubble law, taking the Hubble parameter at Planck scale, this is dynamics. Because in that case, Planck uses the Einstein field equation, while in order to set the Hubble parameter at local scale, you need the kinematics of some objects like galaxies, like supernovae, and so on. So in comparing dynamics and kinematics, it could be very different. So this is the point. So we have to understand. I don't think that is a problem of some new physics. It's a problem of how to understand what is going on.
Thank you very much, Salvatore.
Your question.
Anyone else? Yeah, if not, I wanted to ask. So Okay, yeah, cosmography indeed. I mean, it's a great it's the simplest method. I mean, it's just an expansion of the scale factor, and it does not introduce any bias towards any particular cosmological model. But I mean, if you prematurely truncate the series, then this may induce like numerical errors at higher redshifts. And then if you consider higher order terms, then you get some doubts on the convergence of the series, right? So and you said, of course, if you substitute Taylor with Padé or with Chebyshev, you can overcome, for example, convergence issues.
Right.
But yeah, my question is, like, is there any clear consensus on the exact number of terms to consider in order to somehow faithfully mimic the underlying cosmology?
I can say you this in general. This is, thank you. This is a very important issue. The general consensus. We start to discuss this. I can say you the story. The story is I was in a conference in Poland some years ago, and I met some very nice colleague which was using the Padé series in order to understand what is going around the event horizon of a black hole. Because in that case, you have a convergent problem, which is exactly the same that we can have in cosmology. And what he found out is this, that the Padé series can give us the way in which you can answer exactly the question by Weinberg. So the convergence of the luminosity distance give us the information that you need in order to have a good model, essentially. So the consensus essentially is this. Imagine that you have a Padé series, and the Padé series, you have the numerator is one order larger than the denominator, the denominator. If it is converging, it is a good. It can give us a good luminosity distance. Otherwise, you have to be careful because you can have some divergence, as you said. Chebyshev could be better in this perspective because in Chebyshev you can give step by step the cosmological ladder that you have. So in Chebyshev you can say, for example, imagine that you want to reconstruct the cosmic history from here up to a redshift of the order 10. In that case, you need some distance indicators that are very different. For example, here you need Cepheids. At certain point, you need supernovae. Another point, you need BAO. After, you need quasar. After, you need GRB, and so on. In order to control this step by step, this staircase that you have, what you need is that the step after your seminar, your cosmographic series should be controlled. In Chebyshev, this is possible. Why? Because Chebyshev is a series of orthogonal polynomials. So you are normalizing step by step the series. So in that case, you can have a control of what is going on, and you can avoid the divergency. While in Taylor, you cannot do this. Immediately, you can see that in Taylor, as soon as you are reaching a redshift of the order 1, your information is going to be lost.
Mm-hmm.
So the general criterion is that trying to find out polynomials where you have a convergence of the ratio, essentially.
Yeah.
This gives us information which could be good in order to reconstruct some reliable models.
I see. Great. I don't know if there's any other question. Let me stop the recording here.